It turns out that this result that we talked about earlier had another application. The result that when A has reduced echelon form R, there exists an invertible P such that PA is equal to R. Furthermore, when A is invertible, the reduced echelon form is the identity matrix, and P is precisely the inverse of A. This result can be used to compute A inverse using Gaussian elimination. Let's see how this can be done. Suppose we have a n by n matrix here. A is n by n, C is n by p, and suppose we form the augmented matrix A and C. So this is an augmented matrix. Now suppose we can find an n by n invertible P such that we multiply P here. At the right hand side we get an identity matrix. In place of A matrix we get an identity, and in place of C matrix we have a B matrix here. First question, is A invertible in this case? Let's first write down what we know. At the left hand side we have PA. The left hand side becomes PA and PC, and the right hand side is still the identity and the B. So we have PA equal to the identity and PB equal to PC. If PA equal to identity, what does this mean? That means A has an inverse and the inverse is equal to P. And if P is equal to A inverse, B, which is PC, would then becomes A inverse C. And we know that the P matrix will correspond to the product of elementary matrices in performing Gaussian elimination on A. So we haven't really made the connection between Gaussian elimination and A inverse, right? So let's consider the special case that C matrix is the identity matrix. We can always choose the C matrix to be identity matrix right here, right? We can put identity here, right here. Then B matrix, which is equal to A inverse C, A inverse identity, will be A inverse. So what this means is that if we apply Gaussian elimination on A matrix and identity matrix, then in the end, what we get at the right-hand side, the first part is the identity, and the second part, B matrix, will be A inverse. So by performing Gaussian elimination on this augmented matrix, what we will get would be A inverse. Another implication of this result is on solving multiple systems of linear equations. Suppose A is n by n invertible, and we have k systems of linear equations. So we have AXB1, we want to solve this system of linear equation, and we have AX equal to B2, we want to solve this system of linear equation, all the way to AX equal to BK. Can we solve these k systems simultaneously? That means we only need to solve it once and we get the solution, all the solutions. To solve a system of linear equation, we apply Gaussian elimination, right? So let's say we form the augmented matrix. We have A and B1, B2 to BK. So now this would be n by n plus k matrix. Okay, and now we apply Gaussian elimination on this augmented matrix. So P will represent the elementary raw operations we apply on A to get the reduced echelon form, which is the identity matrix because A is invertible. And on the right hand side, what we will get, the remaining part of the matrix will be PB1 all the way to PBK. Since A is invertible, so we know what P is, right? What is P? P is A inverse. So PBI is simply A inverse BI, which is the solution of AX equal to B. So by applying Gaussian elimination on this augmented matrix, we can obtain the solution for the K system of linear equation simultaneously. Let's go back to a corollary in section 2.3. Suppose we have an augmented matrix A and a vector B. The reduced row echelon form of the augmented matrix is R and C. Then AX equal to B and RX equal to C, they have the same solution. This is a result that we had promised in section, we had promised that we were going to show in section 1.3 when we talked about solution of system linear equation. What does this corollary mean? Let's say this is a system number 1 and this is a system number 2. What this means is that if V is a solution of 1, then V is a solution of 2, and vice versa. If V is a solution of 2, then V is a solution of 1. So if we want to show that these two systems have the same solution, then we need to show both ways. Let's first start on some facts that we have already known. We know that this is the reduced row echelon form of this. So we know there exists a P, invertible P, such that PAB is equal to RC. This means in particular that R is equal to PA and this C is equal to PB. Now suppose that V is a solution of 1, of system 1. If it's a solution of system 1, then of course it satisfies AV equal to B. Now we want to show it also satisfies system 2. To make a connection with the system 2, let's multiply P on both sides, P on this side and P on the other side. PA is equal to R, right? And PB is equal to C. PB equal to C and PA equal to R. There it is. It means V is a solution of Rx equal to C. It satisfies this system linear equation as well. So indeed, if V is a solution of 1, it's a solution of 2. Now let's try the other direction. Suppose V is a solution of 2 of system 2, then it satisfies RV equal to C. Now we want to show it also satisfies AV equal to B. Let's multiply both sides with the P inverse this time, because that's how we can get the A matrix, right? So P inverse C on the right hand side. P inverse R, we get A, and P inverse C, we get B. So there we go. It satisfies AX equal to B. So it's a solution of AX equal to B. Now we have done both ways. If V is a solution of 1, we have shown it's a solution of 2. If V is a solution of 2, we have shown it's a solution of system 1 as well. This corollary turns out to be very useful. Let's ask some more questions, and from the answer of these questions, you will understand why the corollary is very useful. Suppose let's consider the case the homogeneous equation AX equal to 0 and RX equal to 0. Do they have the same solution? Indeed, this corresponds to the case that the B vector is the 0 vector. Indeed, that's true. Now let me ask another question. The columns of A linearly dependent if and only if the column of R linearly dependent? Pause and think about this. Are the linear dependence of the columns of R and the linear dependence of the columns of R the same thing? One if and only if the other is true. That is indeed true, isn't it? Why? Because of the first property. Remember, the columns of A are linearly dependent if and only if the homogeneous equation have a non-zero solution. The columns of A linearly dependent if and only if the homogeneous equation has a non-zero solution. And because of the first property, these two have the same solution. We can conclude that this is true if and only if Rx0 has a non-zero solution. And this is true if and only if the columns of R are linearly dependent. So if we want to determine if the columns of A are linearly dependent, we can look at the columns of R, which are much easier to observe linear dependency because of the special structure of the columns of R. Let's look at one example to see why this property is very useful. In this example, n equal to 4. So A has 4 columns, A1, A2, A3, A4. R has 4 columns, R1, R2, R3, R4. Suppose V equal to 1, 1 minus 2, 0 is a solution of the homogeneous equation. Alright? So the homogeneous equation has a non-zero solution. This means in particular that the columns of A are linearly dependent, right? And also the columns of R are linearly dependent. So we have AV equal to 0 if and only if RV equal to 0. And we can write down the column vector of A explicitly, A1, A2, A3, A4, and the column vectors of R explicitly. For this matrix vector product, we have A1 plus A2 minus 2 times A3, and this is the zero vector. The linear combination gives us the zero vector. This is true if and only if, for this side, the equation is exactly the same as these, except that A1 is replaced by R1, A2 replaced by R2, and A3 is replaced by R3. So what does this mean? Well, this equation, it tells us that A1, A2, A3, they are linearly dependent, and this is the set of linear combination coefficient that would give us the zero vector. And the same linear combination coefficient of the R vector will give us the zero vector. More precisely, what this means is that the linear dependency among the columns of A and that of R have a one-to-one correspondence. If these columns are linearly dependent, A1, A2, A3, then so are these column vectors. If these 3 column vectors are linearly dependent, then these 3 column vectors, A1, A2, A3, will be linearly dependent. They have the zero vector using the same linear combination coefficient. And this is the column correspondence property. If A is an n by n matrix, the reduced row echelon forms are A has n columns, R has n columns, and Rj, the jth column of R, is a linear combination of other columns of R, then Aj is a linear combination of other columns of A using the same linear combination coefficient, and vice versa. Here's one example that we have seen before. A is this matrix, and the reduced row echelon form R is this matrix. And from what we have derived before, the pivot columns of A are A2, A3, and A5, and R2, R3, R5, R2, R3, R5 are standard vectors, and they contain leading entry. So correspondingly, the pivot columns are 2, 3, and first question. Are the pivot columns of A linearly independent? Pause and think about this. Ready to give your answer? Can we use the column correspondence property to answer this question? If we want to know if some columns of A are linearly independent from the correspondence property, look at the corresponding column of R and see if they are linearly independent. Let's form linear combination of the pivot columns of A. So we have C1 and C2 and the C3 at the position 2, 3, and 5. By setting the other entries to 0, we will then be looking at the linear dependency of the columns of column 2, 3, and 5. This is true if and only if R, the matrix vector product, is equal to the zero vector. So we can see that A2, A3, and A5 are linearly independent if and only if R2, R3, and R5 are linearly independent. So the question is, are R2, R3, and R5 linearly independent? Indeed, because they are standard vectors. So this is true. This is always true. The pivot columns of A are linearly independent. Second question, a non-pivot column AI, suppose we have a column AI that's a non-pivot column, is it a linear combination of A1 to AI minus 1? Instead of asking this question, we can also ask if Ri is a linear combination of R1 to Ri minus 1. Right? Because of column correspondence property, these two are the same question. So this is the same as asking if Ri is a linear combination of R1 to Ri minus 1. And this Ri here, because AI is a non-pivot column, so Ri is a column vector of R that does not contain a leading entry. In our example, this is R, and let's take one non-pivot column out. Let's say R4. R4 is minus 1, minus 2, and 0. Minus 1, minus 2, and 0. Can we express it as a linear combination of earlier vectors? And we see this one and this one, right? And indeed, we can express it as a linear combination of R2 and R3. And what is the linear combination coefficient? For R2, this should be minus 1, right? And for R3, that should be minus 2. And this minus 1 here is exactly the same as this minus 1 here. These two numbers are always, this number and this number are identical. And this number and this number are identical. So these two are exactly the linear combination coefficient to get R4. In other words, when we have Ri, we can always, that does not have a leading entry, we can always express it as a linear combination of previous column vectors which have leading entries, which contain leading entry. Correspondingly, if R4 is equal to minus 1, R2 plus minus 2, R3, then we have A4 equal to minus 1, A2 plus minus 2, A3. And the equations are exactly the same, except R are replaced by A now. Summarizing what we have just talked about, we have Theorem 2.4. First of all, pivot columns of A are always linearly independent. Secondly, each non-pivot column of A is a linear combination of previous pivot columns, where the coefficient linear combination are the entries of corresponding columns of reduced row echelon form of A. In this example, the same as we had earlier, A matrix, the pivot columns are A2, A3, and A5. And if we consider the span of columns of A, we now know that A1 and A4 are a linear combination of other columns. And if we remove A1 and A4 from the set, we would still have the same span. So the span of column of A is the same as the span of pivot columns of A. A question? Suppose A is n by n, and the pivot columns are AK1, AK2, and AK raw. There are raw pivot columns. Now, is the span of the n vectors of A the same as the span of pivot columns of A? Pause and think about this. Are the two spans the same? Yes, indeed. Isn't it? Why? Because the non-pivot columns are always a linear combination of pivot columns, so removing them from the set does not affect the span. So if we just have the span of the pivot columns, we can have the same span as the columns of A. Now we have finished 2.3 and 2.4. 2.5 will be left as a reading assignment.